Right now, thousands of commercial flights are crisscrossing the globe, while military operators track hypersonic missiles tearing through the atmosphere at Mach 5. If we relied strictly on our own eyes, we would be completely blind to almost all of this activity. So how does a spinning piece of metal actually detect a stealth bomber in the pitch black hundreds of kilometers away? The answer lies in an invisible web of electromagnetic energy that surrounds our planet. To keep global infrastructure running and defend national airspace, engineers had to figure out how to manipulate that energy. Radar works on two core principles of physics. The first is the echo principle. If you shout into a canyon, you wait for your voice to bounce back. Radar does the exact same thing, but it shouts using radio frequency energy instead of sound. Look at this simplified diagram. Because electromagnetic waves travel at a constant speed, the speed of light, we can calculate exactly how far away an object is simply by timing how long the echo takes to return. The second principle is the Doppler effect. As the target flies toward the dish, it compresses those returning radio waves, which increases their frequency. If the target flies away, the waves stretch out. By measuring this tiny shift in frequency, the system calculates the exact radial velocity of the aircraft. But knowing a target's location and speed creates a new problem. This raw physical data only gives the operator a generic blip on a screen. Primary radar is entirely blind to identity, creating a dangerous situation for air defense operators trying to distinguish friend from foe. Before we can even identify that target, we have to keep track of it, and traditional, mechanically spinning radar dishes are simply too slow to follow modern supersonic weapons. To track supersonic objects, engineers stripped away the moving parts entirely and created phased array radar. Instead of a large moving dish, a phased array uses a flat panel built from thousands of individual antennas. By mathematically delaying the signal from each node, the overlapping waves constructively interfere, forming a focused beam steered electronically in microseconds. This allows a single station to track hundreds of incoming missiles simultaneously. Yet even with this speed, the system still doesn't know exactly what it is looking at. When an unknown aircraft enters restricted airspace and refuses to answer standard radio pings, operators have to extract classified intelligence from the raw radar echoes. Their first method is measuring the target's radar cross-section, or RCS, essentially how large the object appears to radio waves. A commercial airliner has a broad cylindrical body and massive exposed engines. It acts like a giant flying mirror, reflecting a huge, unmistakable signature. A modern stealth fighter uses sharp angles and faceted edges to scatter radar waves away, shrinking its signature to the size of a golf ball. But if the cross-section data is ambiguous, military radars deploy their most sophisticated technique, NCTR. When the radar beam travels directly down the air intake of an incoming jet, it strikes the rapidly spinning titanium blades of the engine compressor. Those spinning blades imprint a highly complex micro-Doppler frequency shift onto the returning echo. Every jet engine model has a specific number of blades rotating at a specific RPM. By analyzing that tiny shift and comparing it to a classified database, the radar computer identifies the exact make and model of the fighter. But these advanced systems still face a strict physical barrier. Electromagnetic waves travel in straight lines, while the Earth curves. This geometry creates a radio horizon. Any ship or low-flying missile beyond that horizon sits safely below the radar beam, completely undetected. To see past this blind spot, engineers developed over-the-horizon, or OTH radar. These systems fire low-frequency radio waves diagonally upward into the ionosphere, a layer of charged particles. The ionosphere bends the signal back down to Earth, striking targets thousands of kilometers over the horizon. Generating these low-frequency waves requires massive infrastructure, demanding sprawling fields of wire antennas that stretch for kilometers. If the goal is tracking ocean traffic, operators use surface wave OTH. Because saltwater is highly conductive, these low-frequency waves actually cling to the surface of the ocean, diffracting along the water to catch ships hundreds of miles offshore. To defeat the geometry of the planet, engineers literally turned the Earth's atmosphere and oceans into parts of the radar machine itself. Radar began as a simple method for timing echoes. Today, it can read the mechanical spin of a turbine blade inside a moving jet hundreds of miles away. It is a continuous engineering arms race against the physical limits of space, speed, and planetary geometry. This invisible net of electromagnetic energy is the backbone of our modern global infrastructure and defense. If you found this breakdown helpful, hit that like button, subscribe, and let me know in the comments what technology we should decode next. Keep studying, and I'll see you in the next one.